This video explores the topic of energy harvesting within the framework of the European project titled Personalized Education in Measurement Science and Technology Empowered by Machine Learning. The aim of this clip is to introduce the importance, core principles, and key techniques of energy harvesting as a fundamental technology for autonomous, self-powered measurement and sensor systems. Today, many electronic devices are portable and battery-powered, including sensor nodes in wireless sensor networks and IoT systems and wearable electronics like watches, glasses, or clothing. These devices share a common limitation. Batteries eventually run out. Lifetime depends on energy consumption and battery type, ranging from weeks to years. Techniques like sleep modes can extend battery life, but replacing batteries is often impractical or expensive, especially for wireless sensor networks with thousands of devices in remote locations. A promising solution is energy harvesting, which represents the process of collecting ambient energy, such as sunlight, wind, heat, vibrations, or electromagnetic waves energy, and convert it into electrical power to self-power measurement and electronic systems. Large-scale solar panels and wind turbines have long done this, but powering small electronic devices requires micro-scale energy harvesters, just a few centimeters in size. While they produce small amounts of power, it is enough for low-power electronics like sensors. Micro-scale systems face unique challenges, requiring innovative designs. Until recently, ambient energy harvesting at the microscale was limited by high-power consumption of electronics. Advances in transistor miniaturization and lower supply voltages have dramatically reduced energy use, with power consumption decreasing faster than device size following a cubic scaling law. Meanwhile, battery technology has lagged behind electronics. Since 1990, storage capacity has grown over 1,000 times, but battery capacity has only tripled. In small devices, batteries take up much of the size and weight, and their slow improvement increasingly limits system design. New storage solutions like thin-film lithium batteries, fuel cells, or supercapacitors offer higher energy density but face cost and manufacturing challenges. This figure presents different types of energy harvesting systems. Photovoltaic harvesters convert solar and ambient light into electrical energy using photovoltaic cells. Solar energy is abundant and can provide the highest power density among common harvesting techniques, but performance strongly depends on environmental conditions, daylight availability, shading, and the angle of sunlight incidence. Thermoelectric energy harvesting converts thermal energy into electrical energy using thermoelectric generators based on the Seebeck effect, where a temperature difference directly generates a voltage. Such generators can harvest energy from body heat, waste heat in automotive and industrial systems, boilers and radiators, solar heat, and natural temperature gradients between air and soil. Mechanical energy harvesters convert the kinetic energy of motion and vibrations into electrical energy. Sources of kinetic energy are widely available, including machine and structural vibrations, as well as human and vehicle motion. These harvesters can be installed in industrial machinery, buildings, floors, transport stations, roads, and even shoe soles. The most common transducers are piezoelectric, electromagnetic, and electrostatic generators. RF energy harvesters convert radio frequency electromagnetic waves into electrical energy. RF energy is ubiquitous due to widespread wireless technologies, with sources including radio and TV transmitters, mobile base stations and phones, radar systems, Wi-Fi networks, and microwave ovens. Wind energy harvesters convert the kinetic energy of moving air into electrical energy. Wind energy is intermittent and highly variable, with wind speeds strongly influenced by height above ground. Near the surface, obstacles reduce wind speed, which limits the performance of small-scale generators, whose efficiency is typically below 10%. Biological energy harvesters convert energy naturally available in the human or animal body, such as body heat, chemical energy from glucose, mechanical motion, and blood flow or pressure, enabling self-powered wearable and implantable electronics. Finally, hybrid energy harvesting systems combine multiple harvesting techniques to operate simultaneously and improve overall performance. This slide shows typical power density values achievable with different types of energy harvesting techniques, as well as the power levels required to supply various types of loads. Among all energy harvesting methods, solar cells provide the highest power density. Table 2 presents the advantages and disadvantages of the different energy harvesting techniques. The architecture of an energy harvesting system consists of an energy harvesting unit that captures ambient energy and converts it into electrical power, an energy storage unit, typically a rechargeable battery or supercapacitor, for accumulating energy, and a power management controller that decides whether the harvested energy is stored or directly supplied to the system. Also, DC to DC or AC to DC converter is needed, since batteries and supercapacitors require DC voltage for charging. Photovoltaic cells and thermoelectric generators produce DC voltage, but usually at very low levels, so DC to DC conversion is needed to boost the voltage. In contrast, harvesters based on vibrations, RF electromagnetic waves, or wind, generate AC voltage and therefore require AC to DC conversion. The harvested and conditioned power is then used to supply other components of electronic or measurement devices such as the sensing unit, microcontroller, analog to digital converter, memory, and wireless transceiver. Energy storage in energy harvesting systems is typically implemented using rechargeable batteries or supercapacitors. Two key parameters define storage performance: energy density, which determines how much energy can be stored, and power density, which describes how quickly energy can be delivered. High energy density enables long operating time, while high power density allows fast charging and high peak power. Ideally, both should be high, but no existing storage technology achieves very high energy and power density simultaneously. The two classical storage devices are batteries and capacitors. Batteries store energy through electrochemical reactions and offer high energy density but low power density, resulting in slow charging and limited peak power. Conventional capacitors store energy in an electric field and provide very high power density with extremely fast charge and discharge, but their energy density is very low, limiting their use to filtering and signal processing rather than energy storage. Supercapacitors bridge the gap between batteries and conventional capacitors. With capacitances on the order of 1 farad, which is much higher compared to pico or nanofarad values for standard capacitors, supercapacitors offer much higher energy density than standard capacitors. They also provide higher power density than batteries, enabling rapid charge and discharge. Compared to batteries, supercapacitors support nearly unlimited charge-discharge cycles, require simpler charging circuitry, do not need complex protection against overcharge or deep discharge, and are more environmentally friendly. On this slide, the comparative characteristics of conventional capacitors, supercapacitors, and batteries are presented. We can see that, in terms of performance, supercapacitors lie between standard capacitors and batteries. To summarize, this short clip introduced energy harvesting systems that collect ambient energy, such as sunlight, wind, heat, mechanical vibrations, electromagnetic waves, and biological sources, and convert it into microscale electrical power for sensor nodes, edge devices, and wearable electronics. We presented the main types of energy harvesters, such as photovoltaic, wind, RF, thermoelectric, kinetic, and biological harvesters. We also discussed the architecture of energy harvesting systems and the energy storage elements they use, including rechargeable batteries and supercapacitors, together with their key characteristics. Thank you for your attention. This video was produced through the collaboration of SS Cyril and Methodius University of Skopje, the University of Niš and Politecnico di Milano, within the framework of the European project Personalized Education in Measurement Science and Technology Empowered by Machine Learning. More information about the project can be found on the project website and LinkedIn page.